Hello everyone. In this video, we're going to continue on with the basics or fundamentals of reinforcement learning series. And we're going to go all the way back to the beginning when I went over the formulation of the TicTacToe game, how to formulate TicTacToe as a reinforcement learning problem. And today, I'm going to show you how to code that in Python, how to set that up in Python. Because in the next video, we'll train our first agent to play the game of tic-tac-toe. So in a previous article, I showcased you how to frame tic-tac-toe as a reinforcement learning problem, particularly in episodic reinforcement learning. Each episode ends in a draw or one of the two players winning. So introduction. In this tutorial, I set up the simulation elements necessary for applying tabular Q-learning in the next tutorial for Agent 1. To simplify matters for this tutorial and to explain the game dynamics as well as the Python code, both Agents 1 and 2 will be selecting controls from the current control space during game evolution randomly with equal probability for each control. So in this setup notebook or setup tutorial for the game, I'm going to assume both agents are irrational. That is, none of them are learning a policy. This is just to get the nuts and bolts together and iron out the details of the simulation. So to start out, you have to import numpy as NP. You need to import matplotlib.pyplot as PLT. And this is a special module I wrote called checkover. This is to be applied after each decision to check and see if a condition for the game being over is met. So I stored that here in this file called from tic_tac_toe import check_over. In the first cell, in the first cell above, we imported the standard Python modules, numpy and matplotlib. In the second cell, I imported my own custom function that I explained that will be used to test the current game state to determine if the episode is over. That is whether Agent 1 wins, Agent 2 wins, or the game ends in a draw. The terminal conditions are as follows. Player 1 wins terminal condition. I thought about the best and simplest way to specify the terminal condition for each episode for each of the three possible outcomes based on the state values and how those may be spread across the tic-tac-toe board. For Agent 1, or Player 1, because when it places its X on the board, that is recorded as a 1 for the actual state. A simple product rule can be used to scan every column, row, and the two diagonals to see if the product of each entry in every row is 1, if the product of each entry in every column is 1, or if the product in every diagonal is 1. If this condition is met for any row, column, or diagonal in some episode, then player 1 has won. Player 2 wins terminal condition. Similarly, there is a simple and best numerical rule for determining if player 2 has won the tic-tac-toe episode. Because I chose to encode player 2's move of O on the board with the integer 2, we can use a simple sum rule to check every row, column, or diagonal to see if player 2 has won the episode. Simply put, if the sum of each entry in any column is 6, player 2 has won the episode. If the sum of each entry in any row is 6, then player 2 has won the episode. Lastly, if the sum of each entry in any diagonal is 6, then player 2 has won the episode. And lastly, the draw terminal condition. For the final possible terminal condition, the draw, we can use numpy's all method to check that all of the state values are non-empty or non-zero to confirm that the episode is over after having checked for player 1 and player 2 victory and confirming neither player 1 This works because we have encoded an empty cell with the integer 0. If player 1 has not yet won and player 2 has not yet won, and we do not have a draw, then the game is ongoing. This covers all of the cases for the checkover function. In the code in that Python module, TicTacToe.py, I implement all of that. So define your function, checkover, and it'll pass in the game state. This is the current board state. And I'm going to determine if the game is won by any player or if there's a draw. And I return true if the episode is over, and I return false from this function otherwise. I also return a string 1 if player 1 is won, and a string 2 if player 2 is won, or a string 3 if there is a draw. So this first set of if statements is checking whether player 1 has won. And you can come back and read this article later. I'm not going to go over every single line of code in here. And similarly, all of these if statements are to check if player 2 has won. You can see I'm using numpy's sum function, and similarly for the check for player 1's condition, you just make sure you can see I'm using numpy's product function to check for those conditions. And then lastly, I check if there's a draw, and then I return this Boolean variable is done and the string, whether the player is won, or it could be a draw. So now we need to discuss basic variables we need to set for setting up the tic-tac-toe simulation. First, I want to keep track of player 1 wins, player 2 wins, and draws. So I define these 3 variables here and set them equal to 0. Then we need to set our number of episodes, which I just choose 10 here. And I have these player markers dictionary. 1 gets mapped to X and 2 gets mapped to O. This is to create a visual representation of the state, a better visual representation. And then here I have my episodic loop, where I loop over for each episode in range num episodes. I then set my isDone Boolean flag to initially be false, because right when you're starting out, the game's not over. I have my controls. I use a set for controls because starting out, each player has a full control set size, but each time when a control is taken, it needs to be removed. And remember, sets in Python are used for unique items only. And I have this initial board state, which is a 3x3 board. That's your tic-tac-toe board. And I set the time step equal to 0. Here's the initial board visualization. I use a dash for an empty cell. And print for episode, here's using f strings for episode, and k equals k, then the board. And the setup for the simulation, we set variables to keep track of the player wins and draw, like I said, and we can also set the number of episodes we wish to play. We start off with the isDone Boolean flag set to false. For each episode, we start off with a full control space and use a set object to hold possible controls each player can choose when its turn comes up, which is, remember, essentially which board position to take. And remember, as the board starts to fill up, the options decrease. We start with an empty board in each episode, and with time at stage 0. I use an array to visually depict the board, with dash being an empty cell, X will be agent 1's move, and 0 or O being agent 2's move. Then I use a Python f string to nicely print data relevant to the simulation. Then the main logic of the simulation is within this while loop. We loop while isDone is not true. So while it's false, we enter in to here. And if k mod 2 is equal to 0, it's agent 1's move. Agent 1 moves first. It takes a random control from the list. I convert the set to a list, take a random choice from it. and I remove that control from the set of all possible controls, reshape the state, the board state, and then I place a 1 down on whatever position agent 1 chose, reshape the board, update the time, print out some information relevant to the simulation, check if it's done. If it's done and agent 1 won, I update player 1 wins. If it's done and player 2 wins, I update player 2 wins. Otherwise, it's a draw. The game ends in a draw. If these conditions are met, the final if. In the above body of the while loop, we run a full episode. The first if block within the while loop is for letting agent 1 make its move. The next code block is for when it is agent 2's turn to move. Similarly, agent 2 has the same sort of logic, so I don't need to rehash that. Here I'm showing a sample output of the board state and this information I'm printing out here, the episode number, the stage number, and the board state. So you can see the moves that are going on. Agent 1 moved in the center. Then agent 2 moved here. It just keeps going on and on until, you can see player 1 won it because it got these 3 X's aligned, and so on and so forth. Just many more games I'm printing out. From this, we can see that there is indeed a good mix of 3 possible outcomes. For the first part of this simulation, I increased the number of episodes to 10,000 and print the number of times agent 1 won, agent 2 won in the episode in a draw. So from this, we can see that there is clearly an advantage of agent 1 moving first, because using both agents using these equally likely or random policies, stochastic policies, we can see player 1 had 6,800 wins. Meanwhile, player 2 had 1,940 wins. And lastly, there were 1,260 draws. So when both agents are using a uniform random policy over the available controls, that is, both players are irrational, non-intelligent, we can see that player 1's first move advantage is quite significant. Also, the episodes end in a draw roughly 10% of the time. That's it for this video. Don't forget to hit the like and subscribe button. Next time, you'll see and learn your first reinforcement learning algorithm applied to the game of tic-tac-toe. So it'll all start to come together. One of the agents will be made intelligent. And if you want to read this article and not miss others, I encourage you to subscribe and join Medium today.